Hi there and welcome to the screencast of the first workshop for 161.324 data mining. If you haven't met me yet, I'm Jonathan. Okay, so I'm going to go into the first week and we will find the first workshop, and I'll just click on that. So we're looking at ggplot2 and dplyr. And here it is here, and then I will read through all of this. I will install R&R Studio if I haven't already, with the link there. And then I will download the workshop sheet. So I'm going to right click and save that somewhere useful. So I'm going to put it somewhere in here. Okay, and then I'm going to go into RStudio and load up that file. So I go open, find that folder and load the workshop. Okay, I'm going to get rid of this console window because we won't be needing this. And I read through, so we're going to be looking at the basics of ggplot2 to produce charts and dplyr for manipulating data. So if you haven't done much using the tidyverse set of packages, so that's things like ggplot2 and dplyr and tidyr and so on and so forth, then I highly recommend you spend some time looking into tidyverse a bit more. So one potential resource for this would be the, if we go back to stream, under the course resources, there's the R for Data Science book. So if you click on that, then this is written by Hadley Wickham, who is the original author of a lot of the tidyverse packages. So for example, we've got data visualization here, which is ggplot. Okay, so there we go, telling you all about how to do stuff in ggplot. Data transformation is then what we're doing also today with dplyr. Okay, so that's what the some other material for you to have a go at if you find that you're not getting to grips with it based on this workshop. Okay, so the first thing we note is that before we start, we should knit this document in RStudio. So remember, this is a markdown document, so it combines narrative text such as the code, such as the writing here, which has various formatting. So we've got a heading here, level 2 heading with two hashes for a level 2 heading. Further down, we'll have a letter 3 heading, I think. Here we go, level 3 heading down here with 3 hashes. We've got some item stuff, and so on and so forth, right? We've got some various formatting and stuff, and we've also got code blocks. So when we run this code, it will put the results in line. So we'll start by knitting. And it seems as though I need an updated version of Markdown. So do I want to install this package? Of course I do. Thank you. So it will go and install that package for me. Hopefully there won't be any issues here. There we go, and away it's rendering now. And so you can see this creates an HTML document that has all our code and all the output inline in it. So make sure you can do that before we start, and then you can go through and try everything out for yourself, and then that just ensures that if you get any mistakes when you knit it, it's your fault, not my fault, right? So any errors during knitting are just because it's an error that you would have made, and so that will help you debug it. It's not something that was there when you first got the document. Okay, so this first code chunk is loading the tidyverse set of libraries. So notice that we've got a whole bunch of output here. It tells us that it's attached to a series of packages. 8 packages: ggplot2, tibble, tidyr, readr, per, dplyr, stringr, and forcats. And so these are all sort of the default packages that are loaded when you load the tidyverse package. So the tidyverse package is called a meta package. So its job is just to load other packages, really. And the ones that we'll be using today are ggplot2 for charting, dplyr for data manipulation. I think we'll use some stringr as well, which is basically operations on strings. So things like manipulating strings, extracting substrings from strings and stuff like that. We'll be using readr for reading in some data later. And we'll be using tibble because that's basically what we're going to use to hold our data sets. So our data sets will be data frames, but they'll actually be tibbles, which are data frames that have a a particular form. I don't think we'll be using forcats, which is for manipulating categorical variables, and we won't be using per or tidyr, but we will use tidyr next week. Okay, so the other thing to note is that you've got some conflicts here. Okay, so this is just something to be aware of. So there are some functions in the dplyr library called filter and lag, and they are going to be masking the existing functions, filter and lag, which are from the stats library. So base R, so when you load R up, it includes the stats package, which includes lots of stuff like fitting linear models and all sorts of things, correlation and all that sort of jazz. And that contains a function called filter and a function called lag. Okay, dplyr also contains a function called filter and a function called lag, and because we've loaded dplyr up via the tidyverse, the dplyr versions of filter and lag have overridden the stats versions of filter and lag. So in this case, it's what we want, because we're going to be using dplyr filter, and it works very differently than base than the stats filter command. So we definitely want this to happen. But it's just something to watch later when we get more and more packages involved, that you may end up with something overriding a function later, and that might mess things up. So a really, really common one is if you load the mass package, so MASS, we'll be loading that later for doing linear discriminant analysis, I think, when we do classification. And that has a command called select, and dplyr also has a command for select, and you almost certainly want the dplyr one, not the mass one, when you're using the command select. So if you load mass after you load dplyr, then you'll find that you'll get the mass select function when you type select, and you'll get some odd error. And the error is because you're using the wrong version of that function. Okay, so it's just something to keep in mind. It's not something to panic about. We've also loaded the Palmer Penguins package. You may have had to install all of these. Hopefully that went without issues. Essentially, this is so that we can have some data on penguins. So here it is here. So we've got 344 observations of individual penguins where we have some measurements taken on the penguins. Okay, the year is measured, the sex, the body mass, the flipper length, build depth and build length, and the island and species. Okay, so we're going to use this for plotting. And so here's our first chart. Okay, so we've just done a simple scatter plot of, let me get rid of this so it's a bit bigger, of flipper length versus body mass. And we see there's the relationship that you would expect. Penguins with bigger flippers are heavier, which is kind of sensible. Notice that there's actually two pieces of output here, so we've got a warning here saying that it's removed 2 rows containing missing values. Okay, that's nothing to be worried about. It's just that for some of these penguins, one of these two variables, or at least one of these two variables, has not been measured. So of course we can't plot that point, and it's just telling us about that. So the recipe for ggplot, hopefully you will have all seen that before, but perhaps some of you might not have, depending on when you did 200 level courses in stats, and even 100 level courses in stats. So it follows the same recipe where you go ggplot, you then specify some data, so in this case it's the penguins data frame, and then you add on a number of layers. So we're adding on a layer of points, so geom point, all of the layers start with geom, which is short for geometry, and then you set up a mapping which sets up how you go from features of the plot to features of the data. So we've got X, which is a feature of the plot, the X-axis, should be mapped to the flipper length in millimeters from the penguins data set. So this is a column name. And the Y should be mapped to the body mass. And that, of course, is what we get. So there's the recipe. We'll be reusing the recipe over and over and over. Okay. So let's try some things out. Let's try adding color equals purple as an additional argument to geom point after the mapping argument. So for some of you, this will be sort of revision that you know. Feel free just to sort of go through it really fast. That's fine. I'll go through it all anyway. We'll start on the new exciting stuff probably in week 3. although there may be some things on missing values next week that you may not have seen before. Okay, so we'll just take the same code that we did and we'll just do what it says and try adding color equals purple as an argument to the geonPoint. So so there's already an existing argument to geonPoint, which is the mapping argument. And now I'm adding an additional one, color. So I've just put a comma there to separate those two arguments. So sure enough, every point is purple. Excellent. All right. Let's have a look at the next one. Try adding color equals purple as an additional argument to AES inside the geonPoint. So instead of putting it here as a separate argument to geonPoint, we're going to put it as a separate argument to the AES. So we're going to put our color equals purple in here. Okay, let's see what happens then. So what we get is we get something that's not purple. In fact, we get sort of a reddish hue, and it helpfully gives us a guide over here telling us that red is actually supposed to be purple. Clearly this isn't correct, right? What we've effectively done here is, because we've put the color argument set to purple inside the aesthetic, the AES command, then what it's looking for is it's looking for a column in the Penguins data set that is filled with purple. So essentially when we say that color equals purple, essentially what it does is it adds a new column to the Penguins data set and sets it as purple for every entry. Now clearly that's not what we want, because it's every entry has purple in it, it's treating that as a grouping variable, a categorical variable, and it's then saying, okay, I will note that we've coloured by the grouping variable here, but we've only got one group and the group's name is purple, and so I will just tell you that. And of course the actual colour that I'll make the points will just be the default colour when you've got a categorical variable which is red. Okay, so if we want to set the colour of points, then we need to do that outside the AES. Okay, if you want to set the colour dependent on the data, so allow the colour to change with the data, then you put it inside the AES. Okay, so when it's inside the AES, it's part of the mapping, right, of features of the plot to features of the data. When it's outside the AES, it's setting. So this one up here is setting. So and this one here is mapping. So let's just write a little bit about this. So if we put color equals purple inside the AES, then it's adding a new column to the data and mapping the color aesthetic to that new column. As the new column is a categorical variable, just a bunch of labels, ggplot will color by that categorical variable, but all entries are just purple, which means they're all part of just one group called purple. This is mapping the aesthetic to our data, which is definitely not what we want to do. Instead, putting it outside the AES command, but inside the geonPoint command would have been setting the aesthetic as we did in part number one. Okay, so that's the difference between mapping an aesthetic and setting an aesthetic. So mapping goes in the AES, setting goes outside. Right, so try mapping the color aesthetic to the species column of the penguins data. So we'll just grab that same code block. So we're mapping, so we need that oops, somehow I got it down there. Okay, and instead of making them all a new group called purple, we're going to use the species argument. And so there we have it there. So this is actually really interesting in that most of the trend that we saw in this plot, you know, we assumed was a relationship between flipper length and body mass, which is sort of intuitive, but actually it's been driven largely by the fact that you've got different groups, different species. So while within each species there is a relationship between flipper length and body mass, it's probably not as strong as the relationship that you see if you ignore species. Okay, so it's just something to watch out for there. Now, one thing we note from this chart is that we've got these vertical lines here. So we've got banding. Okay, and that's because flipper length in millimeters is only whole numbers, and in fact body mass is only whole numbers too. Okay, so potentially, because we've got whole numbers here, if you've got two observations with the exact same whole number for the x and the y, we may well have multiple observations stacked on top of each other here, and we can't tell that because the points are opaque, right? We can't see through the points, so we can't tell, you know, how many points are stacked on top of each other. And so there's two potential ways to look at that. One is jitter, and one is by setting some transparency. So let's have a look at that. Perhaps we'll use the one that isn't coloured as a starting point. So we'll take this original one. So we'll add some jitter. So all we do is we change the geom point to geom jitter. And all that does is add a bit of random noise. So there it is there. Okay. And what you can see here is there's some points here that are actually very close together, and they used to be on top of each other. I think this series of points in here somewhere, I think, used to be on top of each other, but now, because we've shifted them all a little bit, they're not on top of each other, but they're near each other, right? So this allows us to see where we've got multiple observations a bit more clear than the previous than the graph without the jitter. Okay, so in this case, it's probably doesn't make a big difference. But often, if you've only got a few values on the x, so if say you only had 10 or 15 different possible values on the x-axis and the y-axis, then you could potentially have thousands or tens of thousands or millions of data points on the graph, but it would only show a small number because you've only got sort of 10 or 15 combinations of 10 or 15 possible values of x and 10 or 15 possible values of y, so only a couple of hundred different combinations of x and y are possible. And even though you might have 1 million points, you can only see 200 of them, right? And you don't know where the trend is because all you see is 200 points in sort of a squarish shape. So by adding jitter, you would move those data points that are stacked on top of each other a little bit and allow you to see the ink density, so allow you to pick up what the trend is. The other way we can do that is through sticking with geom point but adding some transparency. So we want to set the transparency because we don't want it to change per point, we want it to be the same for all points, and we can do that with alpha, so say setting it to something, I don't know, 0.5. So 1 is opaque and 0 is transparent. So there we go here. So you can see here that here's some observations that are in fact stacked on top of each other. Okay, because they're darker, right? Each point is transparent so we can see through them, so when they're stacked on each other they become more opaque because we've got sort of multiple layers of semi-transparent glass, if you like. So it becomes darker. Okay. Okay, I'm going to move that code chunk down to where it says to try that. Okay, let's try both at once just to see what happens. So we could add the alphabet to the jitter. Okay. So the alpha doesn't really, I mean, the alpha sort of helps a little bit, because while the jitter is random, so sometimes the points don't move very much, so you still see a little bit of ink density where we've got multiple points that are sort of overlapping each other. The amount of jitter you can change if we look at the help for jitter. So let's have the help for jitter, and we see that there's a width and a height argument. So what are they? Width is the amount of vertical and horizontal jitter. The jitter added is added in both positive and negative directions, so the total spread is twice the value specified here. If omitted, defaults to 40% of the resolution of the data. So that means that jittered values will occupy 80% of the implied bins. So what it does is it works out sort of the minimum distance between observations. So in this case, it'll just be 1 unit, and so it'll be jittering by up to plus or minus 0.4. So we can change that by specifying the width argument. So we could say width equals 10, say. 190 might be a bit much. Okay, so you can see that it's jittered a whole bunch more. Right? So the more we jitter, of course, the more we lose some of the actual underlying structure in the data, because we're actually moving points up to plus or minus 10 in the flipper length and in the body mass. Okay. I seem to remember that that if you don't specify height, then it will just use the width. Anyway, that's how you alter the jitter. Okay. So we use the width argument to the amount of jitter. Okay, so in this example, we use just one geometry layer. So we've used a point layer or a jitter layer, but just one of them. But we can have multiple ones just by concatenating them together with the plus operator. And so here we've got the points, and we've added on a smoother. So by default, the geom smooth will have put a smooth trend through. I think it's using a low S. Yes, using a low S, so it tells us about it. So this is a local linear smoother. So essentially what it does is at each point it sort of considers the points around it and fits a straight line. So like a straight line regression. But that straight line regression is allowed to vary because, of course, the points vary. Okay, so it sort of forms a curve instead of a pure straight line. You can do a pure straight line if you really want to. So that's how you add multiple things. But notice that we've got some repetition in the code here, and that we've specified the exact same mapping twice. Okay, so because that's inefficient, we can move the mapping argument into the ggplot argument, and then it will inherit into the other two layers. Okay. So you can put the mapping as an argument to ggplot, and any other layers that you add on will just inherit that mapping. You can override the mapping if you wish. So for example, down here we're going to add a mapping to geom point to map the color of the points to species. So let's do that. Right, so in the geom point we're going to add a mapping to color by species. Then the points will color by species, but the smooth will be taken across all of the data. Okay, so because the smooth isn't being broken down by anything. The smooth is just inheriting the X and Y, so it's smooth is across all the data. The points are inheriting the X and Y locations of the points, but is also specifying the color. Okay, and alternatively, we could have just put that color mapping back in the in the ggplot. Oh, we don't need the AES again, do we? Just put colour equals species in there and then remove the mapping from the point. And then, oops, I've obviously made a mistake there. I'm missing a closing bracket, aren't I? Then we'll get individual smooths per species. Okay. The grey bands here are the uncertainty. So you can see we've got a lot more uncertainty here because, of course, we're smoothing over a smaller number of data points. Okay. Right, some other things. So that's scatter plots. We've got a histogram, obviously. So this is a histogram of the flipper length. Remember, for a histogram, all you have to define is the x variable, because the y variable is then defined for you. It's just going to be the number of penguins that have that particular flipper length. Okay. By default, you can see that it uses 30 bins. So you can see stat bin using bins equals 30. Pick a better value of bin width if you wish. Okay, so for example, we could try bins equals 20, and that's going to use fewer bins, right? So it'll give you a chunkier histogram. Okay. Other options for looking at the distribution of a single variable is a density plot. So this would be a kernel density. So there it is there. So this is like a smooth version of a histogram, right? So you can see you get the same shape, but you've got less of the problems that a histogram has. So in a histogram, you have to specify the bin width and where the bins start and things like that. And the shape can change quite a bit depending on the bin width. And it's always this sort of jaggy shape, right? Because it's been discretized. A density sort of smooths over those jagginess. You still have to specify the bin width as essentially the equivalent of the bin width, which is the bandwidth. But at least it gets rid of the jaggies, right? So you can see that there's essentially two modes here. You've got a mode of around 190 and another mode of 215. And of course, if we look up here, this is going to correspond to the Gentoo species and then the Adelie and chinstraps. Okay, try mapping colour or fill to the species of the density and histogram. Okay, right, so let's do the density first, which is the one that turns out to be nice. So we could just put the fill in here, couldn't we? So that's what happens if you use the fill argument. So it fills in underneath the density. So you can see here that this hump here that we had was coming from the Gentoo penguins, whereas the other hump was a combination of these two. We could add some transparency to that to help see what happens behind them. So you can see that they are clearly overlapping. You can also use colour instead of fill. So if you use colour instead of fill, then it will colour the outline. Right. So colour for the lines, fill for underneath. I like the fill here. Gives a nicer plot in my view. What about the histogram? Let's do the same thing. We don't need the alpha. Let's stick to fill. Okay, so what it's done is it has coloured in the histogram, right, by species. Now, there's a subtle difference between these two. This one is the same shape as if we hadn't coloured it. So let's do that as well, just so we can compare them. Let's remove the fill equals species. We'll run them both. So you can see here we have these two charts, and the shape of these is exactly the same. Right, it goes up, down, like that. Exactly the same. And so what I infer from that is that the overall count is the count across all species. So this is actually, the height here of 29 is actually the sum of the green, the chinstraps, and 25, which is 4 by the looks, and 25 red ones, 25 Adelie penguins. right? So the histograms have been stacked on top of each other. So we can't actually nicely define the shape of the red histogram, because the shape of the red histogram is starting on top of the green one. It's not starting at the baseline. Okay, so you can change that by using the position argument. So let's do another one down here. Where we're going to use the position argument. And I want to use the identity mapping for that. And so here you can see I've got a different shape. So let's compare this one to this one. They're roughly the same, aren't they? But they are a little bit different. Look at the peaks here. And that's because what's happened now is that the red curve is actually starting at y equals 0. The green curve is always starting at y equals 0, and the blue curve is starting at y equals 0. And they've just been pasted on top of each other. So we've drawn the red curve first, then the green one on top of that, and then the blue one on top of that. So the red curve goes down behind this green one, and the green one goes down behind the blue one. We can't see that, of course, but we could see it if we added some transparency. So here you can see the overlap between the green and the red is that darker green colour. There's the natural green colour there. Okay, so you can see the green goes up to here and down to there, and the red looks as though it goes up to there, perhaps. Maybe up to there, in fact. Okay. So this is more similar to the density curve that we had before, because the density curves start at 0. Okay. What can we do? What other things can we do? Well, we can play with the smoothness of the density. So just like we can alter the number of bins for the histogram, we can also, which alters sort of how smooth it is. We can also do the same for the density. So here's the density there. We can use the adjust parameter, which defaults to 1. Bigger numbers will be smoother, smaller numbers will be spikier. So let's do a small number. There's a spiky one. Clearly too spiky, right? We're introducing a lot of noise here that is not helping us estimate the distribution of the flipper length on each species. And if we go the other way and have a very big smoothing adjustment, then it over smooths the data, and all you get is these sort of normal distributions, which aren't reflective of the true distribution. Okay, so usually the density gets things about right. So you can see here we've got this little sort of extra bump up in here that we wouldn't see if we smoothed it too much. Okay, so this is there's no sort of correct value for the amount of smoothing. It's something that you sort of have to. There's a bit of an art form to it, really. So there is some sort of methods for defining the density in some optimal mathematical way. So you can sort of optimize the performance of the density estimator, if you like. But often it's there's sort of a range of values for the bandwidth that work, and you tend to be able to tell that by eye quite quickly. So do experiment. Generally, I just go with what it gives. And this is it's an example of what's called the variance bias trade-off, and we'll be seeing this over and over in the course, right? So there's two main properties of an estimator. One is its bias. So does it get the answer right? So that's bias. So if it gets the answer right on average all the time, it would have bias 0. But if it gets the answer wrong on average, it would have bias, some positive or negative bias, if it's over or underestimate something. The other property is the variance. So the variance of the estimator is, if you like, the performance over time. So from sample to sample, does the estimator do a good job and give you the same result? So if you've got multiple samples from the same distribution and you fit your estimator to those samples, do you get a similar shape, right? So if we decrease the adjust value, so we use a smaller bandwidth, then what we're doing is we're fitting the data that we have better. Okay, so that shape better represents the actual underlying data, because in our data we have these spikes, right? But we have those spikes in the data just because this is a sample, right? And if we got a different sample, then those spikes are going to move. They're just due to random sampling behavior. Okay, so by making the adjust argument small, we are better fitting the particular data set we have, so we're reducing the bias. But a different sample is going to give us a very different picture, so we're increasing the variance. Okay, so by decreasing the bias, we're increasing the variance. Similarly, if we adjust the adjust parameter to a large value, then we're over smoothing, so we're getting it wrong. So this isn't representing well the actual shape of the underlying distribution. We're missing, for example, the little bump that's out here. We're smoothing that over, so we're getting the answer wrong on average. But if we get a different sample and apply the same amount of smoothing, we're going to get a really, really similar result. So the variance here is going to be small, but we're introducing bias. Okay, so all the time we're going to be fighting these two things, right? We're going to be trying to be right on average, so we're going to try and minimize the bias, but by doing so we're going to have large variance, so our predictive performance for a different data set is going to be poor. So we're always going to be trying to trade off these two things, so the bias variance trade-off. And we'll see this over and over through the course. It's pretty much the key thing in data mining. Okay, so let's stick with adjust equals 1. Okay, and lastly, let's switch to a box plot. So again, this is just a matter of changing out the geometry. There we go. There's our box plot. Okay, again, you can put the alpha in if you want. You can switch from X to Y if you want. So instead of X's, you can have Y's. Okay, and it will draw them vertically, up to you. Just like that. Okay, color, again, does the outside of the box plot. Okay, and fill does colors the inside. So up to you. Notice here, though, that because we're colouring by species, the x-axis here is completely meaningless. Right? What does 0, minus 0.2 and 0.2 mean? It's silly, really. The x-axis should be species, shouldn't it? So really, we should add x equals species. We can still keep the colour if we want, although the colour, of course, the guide is not required because now we've got our species along this axis. So we could potentially remove the colour or remove the guide. We'll see how to do that later on. Okay, and the last thing is that we can change things with our labelling. So let's take this box plot and add some labels to it. So let's go. So the x-axis label, I think we don't need it. It's pretty obvious that these are going to be the species of penguins. So let's turn it off by specifying null. The y-axis, we're going to make flipper length in millimeters. Let's add a title. Going to be maybe Gentoo penguins have bigger flippers. There we go. And perhaps a caption. Chart by Jonathan. There we go. Okay, so you can add lots and lots of different things to your chart if you want to. We can also change the label on here. So that's the color, right? So if you want to change the label of a guide, just like we changed the label of the y-axis and the x-axis, these were aesthetics, right? So this is the guide for the color. So to change the label, you change the label for the color. So let's put a capital S there. Okay, have fun playing around for yourself and see how you get on. I'll put that down underneath where it says try yourself. Okay, I'm going to pause the video here and we'll start a new one just so they're not too long.